Good evening, all. Before starting, hi. Before starting with today's session, we can start with any if you have any doubts from the previous week's lectures or anything, or we can start with the concern and maybe you can ask it later. Maybe I'll wait for a couple of minutes if you have any doubts that you want to discuss. Yeah, I don't think if you have any, then we can get started. So like this week's lectures mainly focus on the application of TDMA, like tridiagonal matrix algorithm, and then linearization of the source term. So the first question here is about linearization of a source term. So you can go through the question once. So what we are trying to do, we have a source term given by the form s equal to a minus b phi mod phi. From our, say, when we take the normal 1D heat equation or some diffusion equation, this can be reduced to linear form only when we have SC expressed as SP plus SC plus SP times phi. So only in this particular case we can reduce this original equation into a system of linear equations. So the question asks originally the S is of a form where we do not have a linear form, it is a quadratic form. So in that case, how do you approach? Like in the last week we discussed, so the way we go ahead with that is you take Taylor series expansion around the reference value. So you expand it around some reference value. So S of phi is expanded around phi star. Phi star is the reference value that plus ds by d phi evaluated at phi star, phi minus phi star. So this becomes, say I am just calling as phi star plus ds d phi, since S is given by that, ds d phi will be essentially minus phi minus b phi minus mod phi by phi minus b mod phi, this evaluated at phi star, times phi minus phi star. So this will essentially give you minus 2b mod phi star times phi minus phi star. So now if you group the terms together, so you have S evaluated at phi star. S evaluated phi star is essentially a minus b times phi star mod phi star, and then you have plus 2b phi star mod phi star minus 2b mod phi star times phi. So if I am writing this as SC plus SP times phi, then essentially my SC will be a plus b times So what we are trying to do here is, say you have something like this, 0 to 1 is your domain, this is your domain, and say you have a Dirichlet condition. So on this the value of temperature is 1 and here it is 0, or say phi is 1, here phi is 0. So without source term your solution will be something like this. So now when you have a nonlinear source term, what happens is, now the temperature profile will kind of change depending on your nonlinearity, but the problem is we do not know the coefficients beforehand. So what we do, we start with an initial guess, and then the guess will keep on changing the temperature field. So your profile will kind of gradually evolve. and eventually when you reach your final condition where your phi star is equal to phi actual, in that particular case your SC plus SP times phi will be equals to, or phi actual will be equal to the original function that we have taken. So even though we started with initial guess, like as we go on through iterations, at the final iteration step, the equation we will be solving is the original equation. All the intermediate steps we might be solving different equations, but the final step will be the one that solving the original equation. So the problem, there are many options that we can choose from. So here we have different cases where the screen froze. Yeah. So the choice of SA and SP can be in different ways. The idea here is, since we are assuming a linear form, we need to take as much information as possible from the original function and then pass it on to our iterations. Since for a linear function, the maximum information that you can pass is from the value at a reference as well as its slope. So we will be taking ds by dt as well as SC. So so the first case is essentially says about the case where you don't have any SP term. You essentially just take the SC term. So in this case, we just pass the current information, but we do not tell how the phi value is changing. Like you are not essentially providing information of ds d phi. Say suppose you can have a scenario where, maybe we can take an example. Say suppose you have a very highly or very low thermal conductivity such that your original equation is just this, SC plus SP phi equal to 0 or approximately 0. Essentially your conduction term is negligible compared to your source terms. In that particular scenario, you can directly get your phi p value with this approximation. So what we are saying is, so you have some variation of source with respect to phi, but what we are doing is just taking a linear approximation of it. This will give you some kind of estimate for phi p depending on the problem of what phi is. You need to choose appropriately. Say suppose you have phi as your mass fraction. In that case, you have some physical limits for your mass fraction, as from, say, it should be from 0 to 1. If the limit is from 0 to 1 and your approximation will give you something like this, then you need to change your approximation appropriately so that it falls always less than 1. So we can put a min function such that it will be minimum of this minus s. So you can just take a minimum of minus SC by SP and 1 or something like that, depending on your application. So here we are SP we are taking essentially as ds d phi, but it cannot be always the case. The idea here is we start with some iteration, and this ds d phi should provide us some direction as to how to reach our final convergence solution. You can always take some factor, multiply it with some factor, and then take that as a and use this in our original equation, because eventually when you reach convergence, this value shouldn't affect your final solution. You are essentially changing your way to the final solution, your path to the final solution, but the final solution remains unchanged. So what should this alpha value be? Usually this alpha should be taken to be less than 1, because it's better, the slower you go, the more the chances that you will reach your convergence solution, because if you take much larger steps, you might eventually get diverged. There are some other conditions. So the second question here is also a similar question, but then the difference is here there are two possible cases. Your phi, source term is given by phi minus phi naught whole square. Now how do you linearize it when the case phi naught is positive and phi naught is negative? Okay, the first question should ask is why does it depend on that? So if you have phi as something like this, naturally, as we have done previously, your S we will take as phi star minus phi naught plus derivative evaluated at phi star into phi minus phi star. So this will essentially give SC plus SP into phi, where your SC is phi star minus phi naught square minus 2 phi star minus phi naught into phi star, and your SP is minus 2 phi naught. So like this is the one we have discussed in the previous case. So now the question is, if phi naught is positive and phi naught is negative, there are two possible cases. So do we take the same formulation or do we need to change it? Okay, since I've asked the question, it should be fairly obvious that we need to change it. But why do we have to change it?
How did you get this SC, by the way? Because
SC is essentially the constant one which doesn't depend on phi.
yeah. So in the first case, you're trying to find the value at phi star, is it? No. It's just
Here,
just
okay.
So you expanded it. You wrote it out faster. I think because you were very quick in writing that.
Oh.
Did you?
Yeah, I was okay. So there was a lag in between the display or what, something like that.
No. You just wrote it very fast. But anyways, that's not the issue here. So
okay.
saying that minus 2 phi is the constant. No, this. But phi has. No, the SP has to be. Okay, so the question is, if should 5. I understood what.
So the question is phi naught can like there are two possible. The SP is essentially something like minus 2 phi naught. Now phi naught can be either positive or negative. So will this affect my decision in the choice of SC and SP, or should it not? Or I can use this formulation anyway. It doesn't matter if it is positive or negative.
So I think I will try to answer this. So this S value is essentially goes to our linear system, right? We essentially take that and.
So it goes into your system as.
In the linear system, right? I mean, you actually consider S term in our linear system. Yeah. So we need to make sure that it satisfies the condition, Scarborough condition.
Yeah. So when will it satisfy that?
So the coefficients has to be, some of these coefficients has to be that I forgot actually. So it has some condition.
It essentially says your sum of coefficients with respect to
this coefficient has to be
less than or equal to 1. So essentially it means it has to be bounded.
Correct. So I think you have to take SP value such that this condition is satisfied, so that we can solve. That's what I'm thinking.
So what is the SP condition that will satisfy this criteria? Like from the equation, like this is the usual equation, right? AE plus AW minus, this is the general equation. So with this equation, what is that criteria for SP that will satisfy the Scarborough?
So SP has to be negative. So phi has to be greater than 0.
So SP has to be negative. Or okay, it can be 0 also, but it should be, if it is negative, then the inequality is also satisfied. So in this particular case, your phi 0 should be essentially greater than 0. Okay, if phi naught is greater than, phi 0 is greater than 0, then this formulation is fine. So what do we do if phi naught is less than 0? Like physically there are cases where this can happen.
Okay.
So in that scenario, then this formulation is not the right one to go ahead with. Like if we do this, then cos ZL will just not converge. So we need to change it a little.
This linearization is not correct. That's what we're trying to say. If phi is less than 0, then this linearization is not supposed to be followed for the stable.
Because for stable convergence, you will not get a stable convergence.
So maybe we should take some other linearization. I don't know.
Exactly. So we should take some other linearization. So the one that is reported in the literature is essentially you split your S into two parts. One, the positive one, and the negative one. What I mean is, say you have S equal to phi minus phi naught square. Just expand it. This is a positive part, and then there is a negative part. So like since phi naught is, say phi naught is positive or phi naught is negative, which one is the case? Yeah, phi naught is negative. So what it says is essentially when you split your source term into two components, the one which gives the SP as positive and the one which gives SP as negative. So they are say S1 and S2. What it says is for S2, you just do some slight modification. we just multiply and divide with phi. But here what we do, instead of taking phi, we will just take the previous iteration value, phi star. So in this way you will kind of eventually you will be eliminating the original problem. Say suppose this S1 is the one that has the positive component, S2 has the negative component. So since it is a negative component, that is fine, but for the positive component will go into your SC term, it will not come into the SP term. Our problem is essentially because the positive coefficient should not come into, so maybe I'll write it for clarity. So if this is my SP term, our criteria says SP should be negative. So what we are doing essentially, we are splitting into two parts, S1 and S2. One is positive part and one is negative part. What we are doing, SP should be negative, so this negative part will remain in SP and this positive part will go into SC. That is the only thing we will be doing in such cases. So like even by doing this, what we are trying to do is we will only change the path to final solution, but at convergence we are actually solving at the final iteration step, we are actually solving the original equation, so your solution should not be changing because of this. So if we take our case, we have, if we just expand it, so this we can write it as phi naught square minus 2 phi naught, and then we have a phi naught phi square. So this particular term and this particular term, so this here you have SP as negative, here we are essentially having SP as positive. Like if you write as SC plus SP into phi p, or maybe I'll just write it for better clarity. So this is one term, and the second term is 0 plus phi times phi. So here this is my SC term, this 2 phi, 2 phi naught phi, this is my SP times phi, and here this is my SC. Now if I am linearizing it, this will become phi star, so this will be my SP and this is my phi term. So from our criteria, we need our original case is if phi naught is negative. In that particular case, here SP will be positive. Here, here there is nothing, so this you can linearize normally. So since SP is positive, which we do not want, what we do, we just multiply and divide by phi and then take it to the other side. So we just take the other one, phi naught phi star. Phi star phi will be there, plus phi naught square minus 2 phi naught phi by into phi, or maybe I should group terms together. Square. So we just take ds dphi just to be simpler, so it will be 2 phi minus phi naught star. So what I am saying, s equals phi star minus phi naught but instead we will just write this as phi star minus phi naught square, but this second term will now go into the SC part. So minus 2 phi naught phi minus phi star plus 2 phi star phi minus phi star. So what I am saying, we will just take the value at phi star, so this term goes off, phi star minus phi naught square minus 2 phi star square plus 2 phi star phi. Is that clear? clear. Okay, then we'll go to the next question. So, okay, the third question is again steady state heat conduction problem where you have a source and one. The only difference is previously we have been using just the Gauss-Seidel method. Now we'll be using both Gauss-Seidel, PDMA, and then see what is the difference between these two. So the equation is ddx of k is given as 1, dt dx, and source is given as 2 equal to 0, and the boundary conditions, there is a flux at x equal to 0 as heat flux into the domain is 5, say for domain is, this is the positive x, so at 5 x equal to 0 is 5 I cap, and at x equal to 1, or I should say at x equal to 3 the heat flux is 11 and that is outward. So at x equal to 3 this is 11 I cap. So unlike the previous problem, the only difference is here we are first giving the nodes. So we are giving just 0, 1, 2 and 3. Like previously, whenever we are solving the problems, we have taken phases. We have first divided it into phases, and then we have taken the centroids as the we have taken those centroids as the nodes. But now we are doing it different. First, we will specify the nodes, and then we will give the phases. For the last cell, like for the boundary cells, this is the half cell that we will consider because there is nothing in this other half. So I think by now you are familiar with writing the equations, so I'll just write for say cell 1. Cell 1, the equation goes as T2 minus T1 by delta x. It's T1 minus T0. Maybe, okay. It's equal plus 2 times delta x equals 0. This is for cell 1. So this will give me T2 plus T1, T0 plus 2 times delta x square. Here anyway, like the total, there are 3 units and delta x is given as 1. So I'll just remove this. 2 should be equals 2 times T1. For cell 2 again it is similar. So here you have T3 plus T2 plus 2 equals 2 T2. So now for cell 0, or so we'll take on the left boundary. So we just have half cell. This is my 1 node, this is my other node, this is my 0, this is my 1. And it is told that the heat flux is already given. So heat flux is given as Q equals 5. So if we write for this particular equation for this cell, so this is my west face. So the boundary is just taken as the west face. The other one will be the east face. So here dt dx on the east face minus dt dx on the west face plus here 2 into from west to face. Previously it used to be a full cell, so it will be delta x, but now we just have half cell. It is delta x by 2 equals 0. Now for the east face it is again straightforward. I think I just have to put one more. This is my 1, this is just a face value. 1 is my cell centroid, E is my face centroid. So on the east face it is straightforward, T1 minus T0 by delta x. So what will be this value? dt by dx on the west face. So plus 5 or minus 5. So will it be plus 5 or minus 5? So the flux is given as q equals 5I into I cap. So this is my x direction.
Well, the normal is that way, right? So it has to be minus 5.
So you are saying this will be minus 5?
Yeah, because it is like flux u is in positive y direction.
I've already
And the
written a
normal
minus
is in-
here.
Yeah, then it has to be. Well, wait.
Just give it a dot.
When you take the surface integral, you just do plus and you just do
Yes.
dot product.
Yes, I have written minus
Right.
here because of that. After doing all of
Yeah,
that,
right.
so what
That's
should
right,
this
that's
be?
right. It has to be 5 then. Yeah.
Yeah, it has to be plus 5. So delta x is equal to 1. So what we have here is t0 minus 4. Okay, it should be rewritten in the standard form. So we have t1 minus 4 equals t0, and then similarly for cell 3, like on the right border, we will be having dt dx on the west face, and that will be pointing like say on the west face. This is my 3, this is my west face, this is my 2. So here q is pointing outwards, so dt dx on the west face, okay, this will be the east face, minus dt dx on the west face, plus 2 times half cell volume is delta x over 2 equals 0. So dt dx on the east face will be along the positive direction. It's already taken on the positive, so it is given as 11, minus on the west face t3 minus t2 by delta x plus delta x equal to 0. So the equation we are writing for t3, if we write it, so it will be 11 plus 1, so delta x equal to 1, so we have 12, and then plus t2 equals t3. So if we write all the equations together, so we have for the first cell t0 equal to t1 minus 4. The second cell is 2t1 equals t2 plus t3 plus we have a source term of 2, 2t2 equal to t1 plus t3 plus 2, and for the last cell t3 equals t2 plus 12. So now we have 4 equations and 4 unknowns. So like, since you have to be solving using hand calculations in your final exam, so I thought, and anyway this is a fairly simple thing. So if you are using Gauss Seidel, first step is you start with some initial guess. So this t0, t1, t2, t3. Say you are initially assuming 0 everywhere. So this is your iteration. So if you put iteration over here, so initially at 0 iteration you define everything to be 0. For the first iteration, t0 is given by t1 minus 4. So this gives you a value of minus 4. t1 is given by t2 plus t3, like you use this equation for t1. So it's everywhere 0, 2 by 2 will give you 1. Similarly for t2, now for t2 when you are doing, it should be t1 plus t3 plus 2, but instead of taking 0 you should be taking 1. So t2 will be as 1 plus 3 0, t3 is 0 plus 2 by 2, so that will give you 1.5. And for t3 it's t2 plus 12, t2 is 1.5 plus 12 will give you 13.5. So now again you keep on doing this till you see that these values do not change.
Yeah.
But will
I
it
just want
converge?
to- just want to give some small comment. This is what you're done. You're kind of using the updated values to the Gauss
Yes.
seidel. So this, I mean, just want to. I mean, you might know this, as in just putting it here. Maybe I want to ask something. So it's like this way will converge much faster than if you use only the previous values and
Yes.
update.
Yes.
But I don't think it actually, allows you to do it in parallel, right?
Okay, that is a different issue. Yeah.
No,
It
it's
won't
not.
allow
No,
you
it's
to
a
do.
different
Yeah.
issue.
It won't allow you to do
No,
it in
that's a
parallel.
different issue. But
Yes.
worthwhile to discuss, because updating it might be faster. I mean,
Yeah,
it
but you
might
won't.
converge
Yes,
faster.
you
But
lose
if
the
you do it
ability.
parallel, if you go to GPU, if you have two
Yeah.
use system, I mean, parallel is much
Much
more
faster.
recommended than doing it like this.
Yeah.
Right? You can do it like one iteration. So,
Yeah. If you have access to GPU, then that is the better option.
exactly. That's much better to do it in parallel itself.
Yes. And the method name will be slightly different. Just the name is Gauss Jacobian method. Like it's Jacobi method instead of the Seidel method. The name is slightly different.
Okay, so if you use only the previous
Previous
values, you
values,
call it
Jacobi method.
it's Gauss Jacobi.
Yes.
Okay, if you use this updated, it's Gauss seidel, is it?
Yes, that's it. The name is different. That's it.
That's nice. Okay.
And yeah, if you see in this particular case, okay, just to have a look at these equations. So the first question we have to ask is, are all these equations independent? I mean, we haven't checked that. Maybe we can try to see if they are independent. If you add, say, we'll try back substituting. Say, instead of direct method, we just do some normal substitution. So you know T0 is given by T1 minus 4. So if I substitute back here, 2T1 equals T2 instead of T1, so I will be substituting 2 times T0 plus 4. And then I have T2 equals T1 I already know as T0 plus 4, and T3 is given as T2 plus 12 plus 4. So this will give me T2 equals T0 plus 20. So what do you get here? It's T0 plus 8 equals T2 plus T3. 2 plus T3 is again T2 plus 12 plus 2. So you have 2T0 plus 8 plus 2T2 plus, okay, let's take it that side, 6. Have T0 equal to T2 plus 3. So if you substitute back, T2 equal T2 plus 23. So what just happened? It's like basically it's like if I try to substitute and solve, then essentially what happens is all these set 4 equations are actually not independent. One of these is actually dependent, or you can get one equation from just using the 3 of the other equations. Maybe I can just do that also to just convince you that that is the case. So we'll do it systematically now maybe. So since T2 is given, what we do here, from here we'll take T1 as T0 plus 4. We substitute it back here.
Yeah, actually, if you take T1 or T2 as some constant C,
Yes.
then that's, I mean, yeah, it's fairly, I don't know, you can explain it, but it's obvious for this level of
For 4
course.
equations it might be obvious.
Yeah.
Okay, if it is obvious, then I wouldn't take
Okay.
that extra effort. Yeah, if
No,
it is
that's
obvious,
fine.
actually I've taken
Maybe
smaller
actually
system
people-
so that it will be easy for you to see
No, I
it directly.
understand. That's actually a good question. That's a really good point that you have put. So if it's a 4 system, we're doing it manually and doing like this. Here you have like maybe 1000 cross 1000 system. What properties of such a matrix do you actually look at?
So
to
the
state that
direct
it is
question,
independent or
exactly.
independent?
The question is how is your problem formulated in the first place? You are just giving your flux on as your boundary. So this is what we have discussed previously. If you just give Neumann conditions or just give you the flux conditions at both your boundary points, then your solution is actually not you do not have a unique solution that goes with your differential equation itself. So you have a second order differential equation, and both of your boundary conditions are just Neumann conditions. What I'm saying is you have something like d square t equal to dx square equal to 0.
There could be many solutions which actually
satisfy that particular boundary condition. So only if these boundary conditions are given, then you wouldn't get a unique solution.
Wait, so that is so you have infinitely many solutions when your rank is like
actually less than the size of your matrix, yeah.
Right, less than the matrix. So that's how we need to look at this. So in that case, you so the rank is less than number of dimensions implies few equations are actually dependent on each other, right? Yes. Lines planes fall on each other. That's how actually you.
So how do you go about then to solve such a system? Is to get one new equation. Say if your rank is essentially n minus 1, if n is your matrix size, if this is the case, what you essentially do is you just add one more equation to it so that your rank becomes equal to 1. So you have n equations and unknowns, so you will be able to solve such system. I mean, that's the only way, right?
Yeah.
So physically the problem is, since you have
infinitely many solutions is not something we would, because if you take physically, you have entropy, and only I'm just bringing entropy word just for like, but
okay, we'll just take the temperature. We'll just take temperature.
Yeah, it's actually because of entropy, because you have only one solution. Okay. However, yeah, you have only one solution physically, right?
Yeah. So why is it that happening then in this? It's just because we are just framing it as a steady state problem. We don't know. We don't have the initial condition, but when you take the time dependence, you have something called initial condition from where this information will propagate, right? Now in steady state solution, you don't have any initial condition. So if you are using an iterative method, your initial guess will kind of serve as an initial condition. So like if you take an unsteady problem, you are marching in time. Even in steady state solution, we are iterating using some Gauss-Seidel method. They are similar. I'm not saying they're exactly identical, but it is something similar. That is exactly something similar happening over there.
That is okay. My question is, like for given that equation, it is steady state. Even in other numerical methods, I solve steady state problems. Essentially, you have the single equation, it's no time, like Poisson equation. I don't think Poisson equation has several infinitely many solutions. Maybe if you add a constant, it is.
Yeah, that's what the constant. If the infinity solutions are essentially because of the constant term. You cannot get a unique value of time, temperature.
Like Poisson equation, I can say like 2xy plus x square plus y square is actually solution, minus x square minus y square plus x y is a solution. Plus 1 plus c. You
just add some reference temperature. That is your additional equation.
So what we're saying is, since we are disguising this Poisson equation in our system, so we are also getting infinitely many solutions, including if you include the constant.
Yeah.
So what you're trying to say?
Basically, you cannot determine that constant from this system of equations. That's what I'm trying to say.
Okay.
So you can solve only up to a constant level, but you cannot get that constant.
Okay, so when you say to solve this equation, we have to add another equation.
That is our constant equation. Yes, so that is you need to add some difference. Yes.
Okay. So that constant equation, does that solve some kind of like
no, it's simple. You just put t0 equal to some constant. This one new equation is sufficient, right? You just need some value to fix that constant. It can be anything. You can fix one of the boundary temperatures, or like you'll fix one of the cell nodes to have certain temperature. That should be fine, right? It will solve.
I don't know if that should be fine, but I have seen this hack. It's actually a hack. It's not. How can you put some random value to be 100, right? It's not physical. Okay,
no.
Put some 10,000.
Yeah, it is fine. So see, your physical solution itself is like that. That is some kind of reference you're taking. It's something like for entropy, or say for your enthalpy calculations or whatever you just take some standard as some reference value as 0, and then you proceed with that. It's something like that.
Yeah. So this actually relates to something I have done in SPH, not me, one of my colleagues.
Okay.
So we are solving Taylor-Green problem. If you know what a Taylor-Green problem is, Taylor-Green problem doesn't has any boundaries. It's just periodic flow on both sides. So it doesn't have any boundaries. Okay. The system you get is actually symmetric system. Okay. So even that doesn't have solution just like this. So what in SPH people do is they will take some point. They'll fix it fix some value. Then only they are able to get this. It's no more singular. You make this value by changing that single value to some other constant.
Yeah, understood. It's just very similar to this.
Yeah.
There is some. Yeah. Thank you. So here the problem is because of if you are using a direct method, that is the problem you will be facing. You will have a singular matrix and then you will not be able to solve them. But when you are using an iterative method, you will get some solution because you have some initial guess. So it will converge to some solution. Maybe I'll go through some code to actually show you that works. We will take that at the end of the session. So if you use TDMA, because of singularity, you will not get a solution. If you use Gauss-Seidel, because of your initial guess, you will get some solution. Now, the idea is here you fix some value to one of these cells. When you fix one of these values, then eventually you will get a solution even using TDMA. The question is, if you fix the value, the solution you will get using Gauss-Seidel versus without fixing the value, will both of them be same? They may or may not be same depending on your initial guess.
Can you repeat?
So the question is, so if you are using Gauss-Seidel with some initial guess, it will converge to some solution. You will get some solution. Now, if I fix one of these cells to say 100 and then again repeat the Gauss-Seidel, it will again converge to give some value. So case 1 versus case 2, will both the solutions be same?
Yeah, it should, because essentially here you are fixing one cell to 100. There you are fixing so many cells to some value.
Yeah, so depending on what value of fixed to, it depends, right? So if I fix initially all of them to be 0, the whatever solution I get in final case will be a solution that I get by adding 100 to the previous solution. So like they will be differ by a constant, and that constant will essentially be your difference value.
But these things are essentially converging to some value now.
It will converge to some value only up to a constant, right? It is that function you are saying plus some constant c. That c can vary, right? It can be anything. It is an arbitrary constant.
So what you're saying is this 100 thing will converge to a solution which has plus 100. The 0 then will converge to some value which doesn't has plus 100. But both, like, if you do n plus 1 minus n and you check the convergence, it solves this condition, but they are not the same.
Yeah, so they will have a difference of this c1 minus c2. Oh, this is exactly the one you are discussing now. So slightly reformulated. So you have a rod, 1D heat conduction problem, no sources or anything, but that rod is actually bent into some circular shape, and then say you have welded it together so that now it is a loop. Now in that particular loop, what we are saying is it doesn't have any boundary conditions because you just can't put any boundary conditions there. The only condition is that the last cell should be matching with that the first cell. So maybe I'll just draw it. So you have something like this, a rod. So this is my 0 cell, this is my n cell. What I'm saying?
Is that
yeah.
The fifth problem or fourth problem? Just why?
This is the fourth problem.
Okay, good. Okay, all right.
Okay, bad circle. So what we are saying is now when we loop this, so you have 1, 2, so eventually your nth cell is coinciding with the 0th one. So this is what will happen when you do this. So the question asks you to derive the TDMA for this particular case. So before doing that, maybe you might have already gone through the lecture about derivation for TDMA. So you have equation of this form: A phi equals bi phi plus 1 plus ci phi minus 1 plus ti. This is your equation, provided you have C0 is for the very first cell, for I equal to 0 is 0, and for the last cell Bn is equal to 0. So given this set of equations, how do we go about solving it is, so you have something like A0 phi 0, B0 phi 1 plus T1, A1 phi 1, phi 2, for the last cell Bn is essentially 0, so this is 0, So how did you go about deriving the TDMA algorithm? Is the idea is you kind of substitute from the above equation. So essentially from this equation what we do, we replace our phi 0, like we have phi 0 in terms of phi 1, and use that phi 1 here. So like you already have phi 0 in terms of phi 1, so you substitute this equation into this phi 1. Then you will have phi 1 expressed only in terms of phi 2, and then you go to the next step. So here you will have phi 2, so like from the above equation you already know what phi 1 is. So your phi 2 will now be purely a function of phi 3. So just keep doing this till you have phi n minus 1 given purely as a function of phi n. So now you have phi n minus 1 as a function of phi n. When you substitute it back here, now you will have your equation entirely in terms of phi n. So this is the normal equation. So once you get, like, entire equation will be in terms of phi n, so you solve that equation, you get the value of phi n. Now once you know the value of phi n, since you know the relation between n minus 1 and n, you get the value of phi n minus 1, and then you gradually go in the reverse direction and eventually find out phi 0. So just to get a clarity, so if you see this equation,
your network is giving trouble, yeah. Just now.
I think I just lost the connection and joined again.
Yeah, no problem. Continue.
Is the screen visible?
No, not yet, not now. It was visible. No, not now.
1 second. Yeah, I think now it is visible. Yeah, it's visible. So what we are doing in the first equation, we are essentially writing phi 0 as purely a function of phi 1. The second equation, what we are doing, we are writing phi 1 as so you substitute this phi 0 here plus t1. So now you have phi 0 in essential terms of phi 1, so this entire equation will have two components. So what we are doing, so for any ith equation, what we are trying to do is phi I is represented in the form of phi I plus 1 plus some constant. So these are the constants that we want to find. This pi and this is, say, just qi. So how do we go about it is, we have our original equation ai phi I equals bi phi I plus 1 plus ci phi I minus 1 plus ti. What we are trying to do is substitute phi I minus 1 in terms of phi I, so that this entire equation will give us a relation of phi I versus phi I plus 1. So using the above relation in here, so we get ai phi I equals, we will leave bi phi I plus 1 as such. Now instead of phi I minus 1, I will use the same recurrence relation. So phi I minus 1 will be given by pi minus 1 phi I plus qi minus 1 plus ti. So if I just group terms together, so phi I is given by a coefficient ai minus ci pi minus 1 phi I plus bi phi I plus 1 ci qi minus 1 plus ti. Now say if I compare equation 2 with equation 1, my pi is given by bi by ai minus ci pi minus 1, and your qi is given by so you keep on iterating. So initially we know for the very first cell, for I equal to 0, P0 is essentially B0 by A0, since C0 is 0, and Q0 is D0 by A0. Like we can see it from the first equation. We can see from this first equation. So you keep on iterating the I value till the last cell, and in the last cell what happens? So from this equation what happens in the last cell is for phi n equals, for the last cell you don't have any I plus 1 term, so the first coefficient will be 0 plus you have qn. So once you iterate this, you get the value of qn here, and you substitute it back to get the value of phi n. Now you know phi n minus 1 is given by pn minus 1 phi n plus qn minus 1. So now that you have the value of phi n, you already know these values from the previous iterations, so you just substitute back to get the value of phi n minus 1, and you keep on doing it till you get the value of phi 0. This is the normal TDME algorithm. How is the present one different is because you have this circularity where you have a0 phi 0 equals b0 phi 1. Previously c0 is 0, but now we have c0 into phi I minus 1. So this is my 0 comma n, this is my first one, this is my n minus 1. So when I am at 0, the n minus 1 cell, the I minus 1 cell will correspond to this direction. So that is my phi n minus 1 plus d0. Previously we don't have this term, now we are having this. So the remaining terms will be again straightforward. So a1 phi 1 will be b1 phi 2 plus c1, this will again be phi 1 plus d1. So you have all the equations similar, except for that last equation. For the, say we will write for n minus 2 cell, phi n minus 2 is 2 phi n minus 1 plus c n minus 2, phi I minus 1 is n minus 3 plus di is n minus 2, and for the n minus 1 cell, if you just go for I plus 1, will give you phi n, that is essentially equal to phi 0 plus ci minus 1 is cn minus 1, sorry, ci is cn minus 1, and phi n minus 1 cell, so I minus 1 will be phi n minus 2 plus dn minus 1. Now we don't have to write a separate equation for the nth cell because that will be essentially equal to this first cell. So now you have 0 to n minus 1, so n equations, and you have n unknowns that you have to solve. So from whatever we derived for TDMA, how do we go about deriving the similar algorithm for this particular one? Like, where do we start is again the same process. We try to substitute from the top equations, we try to substitute eventually and go to the bottom, and then we will try to trace back and then obtain all the values before. But unlike the previous one, the only difference here is the first equation, phi 0, previously what we have done, we have expressed phi 0 as in terms of only phi 1. Like, we don't have any term with c0 or here. That's why we were able to do this. Phi 0 expressed only form of phi 1, and then your phi 1 is expressed only as a function of phi 2. Phi 2 is only function of phi 3, so that eventually when we get to phi n minus 1, that will be only a function of phi n, and when we try to substitute back in the last equation, the entire equation will be in terms of phi n, and we were able to get a value for phi n. But now if we see in the present case, if you try to write phi 0, phi 0 will essentially be a function of both phi 1 and phi n minus 1. So when I substitute it back here, phi 1 will be a function of phi 2. Sorry, this is phi 0. Now phi 0 I will express as phi 1 and phi n minus 1. So this will be a function of phi 0 and phi n minus 1. Similarly, if we go to the last one, phi n minus 2 will be a function of phi n minus 1 when I go to the last cell, phi n minus 1 will be a function of phi n minus 2, which is a function of phi n minus 1, and also phi 0. So in the last equation now I will be having another term, so I will be having phi 0 as well as phi n minus 1. So now what I have to do again is I need to get a value of phi 0. So how do you think we start with? Or maybe
Something. Those are the same values, right? Phi 0 and phi
phi 0 and phi n are same. N minus 1 is this particular cell, so they might not be same.
Yeah, of course they are not. Okay, I want you to answer this.
Okay, so like this is the form we have taken previously. So phi I is always expressed as a function of phi I plus 1 times some coefficient plus some constant. Like when we try to substitute back, these are the type of equations we get. But now here it's slightly different. So whenever you try to substitute, you are having both a function of phi I plus 1 as well as phi n minus 1. So if you take phi I as say phi times phi I plus 1 plus you have a phi n minus 1 term always coming up plus Ri. So if I write phi I minus 1 as phi I minus 1 phi I plus qi minus 1 phi n minus 1 plus Ri minus 1. So if I take my original equation, so we have ai phi I equals bi phi I plus 1 ci phi I minus 1 plus di. So say this is 1, 2. Now I substitute this 2 back here. So ci phi I minus 1 can be written as pi minus 1 phi I now if I group the terms, so phi I has coefficient of ai minus ci pi minus 1 bi phi I plus 1 plus you have ci qi minus 1 phi n minus 1 and then some constant terms ci ri minus 1 plus di. So we compare this 3 with 1. So what we are having is pi is given as bi by a minus ci into pi minus 1, and then qi is given by ci qi minus 1 by ai minus ci times pi minus 1. And then you have ra given by the last term, this 1 plus di by ai minus ci times pi minus 1. So for the initial case, when you have say I equal to 0, for I equal to 0 we have phi 0 equals, or say okay, so initially we have a0 phi 0 equals b0 phi 1 plus c0 phi n minus 1 plus d0. So if we compare this equation with our say, now we can compare this, say equation 4 with the original equation number 1. So if we compare equation 1 with equation 4, so you can see like p0 is given by b0 by a0 and q0 is given by c0 by a0 and r0 is given by d0 by a0. So this is fine, but if we keep on doing this, and the final equation we will be getting is a n minus 1 phi n minus 1, or maybe I'll just write first the equations for p n minus 1. So we have phi n minus 1 equals so this is the equation. So this is the equation for the final cell. So in the final cell what we have a n minus 1 phi n minus 1 equals b n minus 1 phi 0 plus phi n minus 2 I can write in terms of phi phi n minus 1 can be written as phi n minus 2 can be written as p n minus 2 phi n minus 1 plus q n minus 2 phi n minus 1 plus r n minus 2 plus dn minus 1. By the time I come to the final state, like I already know how pi is related to pi minus 1 and qi minus 1 is how qi is related to qi minus 1 and ra is related to, so when I keep a for loop over there, so when initially for I equal to 0 I know the value, so I keep on iterating till I reach this I minus 1 cell. So by the time I reach this cell I would be knowing all these values p n minus 2, q n minus 2, r n minus 2, and I already know the coefficients. So if I substitute in this equation, I will get an expression for phi n minus 1 will be a function of phi 0. So I'm not writing the coefficients here, but you will get phi n minus 1 as a function of phi 0. Now what we do again is, now that we know the value of phi n minus 1 from this expression, we will substitute back in the original equation. So original equation goes something like a0 phi 0 equals b0 phi 1 plus c0 into, here we have a phi n minus 1 term, plus d0. Now that from here I can substitute this value back here. So now what I have is I have phi 0 as phi 1 plus some constant. So since this is purely a function of phi 0, once I substitute it back here, I will have again only a function of phi 0. So I'll just take it to the left hand side so that I'll get something like this. So phi 0 will be some coefficient times phi 1 plus some constant. So I'm just writing that as, like in general for any ith cell, if I do this substitution, what I get is phi I as gi times some gi times phi I plus 1 plus some hi. So I'll get something of this form. Now this is very similar to the TDMA form we have derived previously. So if we see the TDMA case, we have taken something of that. So like it's just p and q. Now that we have g and I, that's the only difference. But the equations is of similar nature. So now we follow the same procedure that we did for TDMA. So you just keep on substituting this again and again till you reach the last value. So you have phi 0 as this. So for the last cell you will be getting something like phi n minus 1 equals g n minus 1, or I should write it for the last but one cell. So a n minus 1 phi n minus 1 is b n minus 1. Phi n is essentially phi 0 plus c n minus 2. Okay, sorry, this is for n minus 1 cell, so it will be b n minus 1. So here it will be n minus 1 plus 1 cell, that is the nth cell. For n cell is n equal to 0, so I have written phi 0 plus c n minus 1. Phi n minus 1 is p n minus 2 plus d n minus 1. Now what we do, p n minus 1 times phi 0 plus c n minus 1 to phi n minus 2 can be written as g n minus 2. N minus 2 plus 1 is n minus 1 plus h n minus 2 plus d n minus 1. Now again we know phi 0 as we have written here. So phi 0 will be something as g0, not here, here we have an expression for phi n minus 1 and phi 0. So what we do, from that expression we can write phi 0 in terms of phi n minus 1. So here you will have something of phi n minus 1 plus some constant, plus again you have some constant times phi n minus 1 plus some other constant. I am not writing the expressions. I think it is a little algebraic equation, so you can just solve these things. So you just bring all the phi n minus 1 together, you will have something of this form. You will have all the coefficients of phi n minus 1 to your LHS, so you will have some constant on RHS. So from this you will be able to get the value of phi n minus 1. Once you know phi n minus 1, then you can get phi 0 from here, and then once you know phi 0, you know the relation between phi 0 and phi 1, so you can get the value of phi 1. So like you just keep on iterating. So you know phi 0, so phi I plus 1 you can keep on getting the values for all the values of phi. This is clear? Or do you want me to derive the expressions also? Okay. I assume it's clear. If there are any doubts, maybe I'll post the complete. If we have time, maybe I'll derive this at the end of the session after all the questions are done. So, but the approach is clear, right? The only difference between TDMA and this approach is this particular starting assumption, where in TDMA we will be considering some phi, just phi will be expressed in terms of phi plus 1 and some constant, but in case of a circular one, what we do is in addition to the I plus 1 term, we also have an n minus 1 term, so that is what we will be adding to this. So that will be the only difference. Remaining everything will be similar. The idea is very similar. Instead of one TDMA, you will be doing 2 times. Like you will go from once you come from top to bottom, you will have phi n minus 1 expressed as a function of phi 0 and phi n minus 1. Then again you will go from again you will come from top to bottom, so that you will have phi 0 purely expressed as a function of phi n minus 1. Now since you have phi 0 expressed as phi n minus 1, you will substitute back in your original equation. That will be entirely a function of phi n minus 1, something like this, and then you solve it to get the value of phi n minus 1. Okay, I hope it is clear. So now we'll go to 5th question. Here we have 2 variables, so this is what you eventually have be solving with. Say you have momentum equation which is coupled with, say, your continuity equation. So we'll have 2 TDMAs that you have to solve. So the equations will be something like so you have something like AI Fi given by, this is the normal TDMA, this will be AI times Fi plus 1, Bi times Fi plus 1, Ci times Fi minus 1 plus Di, and in addition to this you will have another term Gi, where Gi is another equation for Gi. So you have AI times Gi, Bi times Gi plus 1, Ci times Gi minus 1 plus Di plus Ei times Fi. So that now you have 2 equations and both of them are coupled to each other. So idea is to use TDMA to solve these equations. So how do you go about it? Like, any starting guesses? Where do you start?
Hey, you have to tell me. I'm not much aware with TDMA yet.
Okay.
I'm learning.
Yeah, okay, it will be fairly straightforward. Like it very similar to if you just make slightly some rearrangements. So if I just take the Gi term to LHS equal to this entire term, similarly I'll write AAGI minus equals this entire term, so that now I can write it in some matrix form, just some shifting. So you just write AI. So what I'm trying to do, just write it in some matrix form. This will be Fi Gi. So what I have here is AI0, and then you have minus Ei, here minus capital Ei, and then will be AI equals, I can write similar way here, Fi plus 1, Gi plus 1. So the coefficients will be Bi 0, 0, Bi. Similarly you have Ci 0, Ci, Fi minus 1, Gi minus 1, and then you have an identity matrix. Maybe I'll just write it as just identity matrix, so you just write Di and Di. So like if you make this rearrangement, if I call this as say xi, that vector as xi, so I have something like this. So ai hat equal to some b hat, okay, some bi hat xi plus 1 plus ci hat xi minus 1 plus di hat. So if you just make that rearrangement, so everything is very similar. So this is again your classic equation, the original equation that we are dealing with. ai phi equals bi phi plus 1 plus ci phi minus 1 plus some constant, some di. So it will be again the same process. So you just substitute back. So you express xi as some pi times xi plus 1 plus some qi. You substitute from, if you start with this and then you write xi minus 1 as pi minus 1 xi plus qi minus 1. Now you substitute back in the original equation. So you have a hat xi plus pi hat xi plus 1 plus ci hat pi minus 1 hat xi plus qi minus 1 hat plus di hat. So now you have very similar equation. So you just take a hat minus ci pi minus 1 hat times xi plus bi hat times xi plus 1 plus ci hat qi minus 1 plus di hat. So if you compare, say this is 1, 2 and this is 3. If you compare 3 with 2, you'll be having ai hat minus ci pi minus 1 hat times pi hat is essentially equal to pi plus 1. Or is it the other way around? Yeah. So if you multiply equation 1, if you multiply this equation with a hat minus ci pi minus 1 hat, if I just multiply the equation number 1 with this and you compare these two, so this is what you get. Similarly, you will have a hat minus ci pi minus 1 hat times qi hat will be your qi plus 1. And similarly, you will get the last equation. Okay. So for the constant also you will be getting. So this is fine. Now you also have with the entire constant term. So ci hat qi minus 1 and then di hat. So give me a second. So if you multiply this with this, bi hat equals bi hat. This is the equation you are getting. So if you multiply equation 1 with this, the coefficient of xi plus 1 here is bi, and this is the coefficient you will be getting in equation 1. So this is equal to bi hat and this is equal to this. So now you know the initial values. For I equal to 0, essentially ci is 0. So the same equations for I, for initial case, for I, for the first node I equal to 0, you have you don't have any ci, both small, little and capital ci are 0. So you just have a0 hat p0 hat equal to b0 hat. So from this you can get the value of p0. It's like this is a 2 by 2 matrix. So this should be, you inverse is where, and a0 matrix is this. This is our a0 matrix. So a0 is something like a0 minus e0 minus e0 and a0. So you can just invert this and you can get the value of p0, or even if you do not invert, it doesn't matter. So the idea is to get the value of pi, like you iterate it. So this is for I equal to 0, and for the next one I equal to, once you get the value of p0 and q0, for next case you already know the equation. So use this equation, you know all the values of I minus 1, pi minus 1 and qi minus 1. So you'll be able to get pi and qi. You keep on iterating till you reach I equal to n minus 1, and once you reach I equal to n minus 1, or whatever is the last, whatever is your last cell, then you, for the final cell, what you have is, if you consider this original equation, so xi equal to pi plus 1 xi plus 1 plus qi hat. So for the last cell, say if it is ith cell is the last cell, you don't have xi plus 1 term, so this will be 0. So whatever you get in the last value of qn hat will be equal to your xn. So now that you know the value of xn, you go into this equation, get xi. So your xn minus 1 will be given as pn minus 1 xn plus qn minus 1. You have already computed the values of q and p, so and you know the value of xn from here, so you substitute here, you get the value of xn minus 1. So similarly you will get a value of xn minus 2 and minus 3 and so on till you reach the value of x0. So it is very similar to TDMA. The only difference is instead of scalars, now you will be having your matrices here when you have coupled equations. Now if you have, like, the size will essentially depend on your number of coupled equations. But in the classes, even in the upcoming, when you do simple and all of that, we try to eliminate these coupled equations in some way. Maybe we'll see that when simple starts. So if we don't deal with coupled equations, we'll try to decouple them somehow. We'll come to that later. So I think this question is clear. Okay, the last two questions I thought of actually. Okay, we have some half an hours. Okay, so you can have a look at the question. So this is the normal TDMA. You just have a 1D case. This is what you will get. In 1D case, you have this is your east cell and this is your west cell. Now the second problem is when you have a 2D case. So this is your, say if this is your east cell, this is your west cell, j plus 1 is your north and j minus 1 is your south. So the second one is for a 2D problem. So the only difference between 1D and 2D is that now you have to deal with two indices. So I think the lectures deal about something called line by line TDMA, not just TDMA, we call it line by line TDMA. The idea here is TDMA is only for 1D problem. Like the equation itself, the way we have derived this, the equation assumes like this particular form, or okay, we'll take the general form. The equation of this particular form, AFEI equals I plus 1 and I minus 1. So it just works for a 1D case. So in a 2D problem, we have to, the way we go about it is just take each as 1D problem. So say we'll fix this line. We'll fix this line, along a line we will do the TDMA, and then what we do along the other direction is we combine it with some Gauss-Seidel method. So what I'm trying to say is, say you have equation of this form, Aij Pij equals, say I plus 1, I minus 1 j, so when we have something of this sort, TDMA works only when you have two things. So what we do, either we fix the j direction or we fix the I direction. So we will take it's something similar to what we are doing for linearization. So we will take the previous reference value and then we will fix our coefficients. So say suppose we will fix the j direction. So what we do in this particular equation, if you are fixing the j direction, this particular term will go with a star, j minus 1 will go with a star. So if you compare this with our original, so this will be something like AI, this will be your PI, this will be your CI, and this all these terms evaluated at that particular phi star will be my DI. So now it is of the normal form as we do for TDMA, so that you can solve this using your normal TDMA algorithm. And then once you solve this, you will update your values of all your values will get updated. You will use the new values of phi star and then again substitute it back. And you keep on doing till you reach your convergence. Essentially your values do not change. The idea is clear, right? Maybe I'll ask, say suppose you can have different boundary conditions, right? So say you have t equal to 0, t equal to 1, and then say you have some flux condition here. There are two ways you can do this, like you can either fix I or you can fix j. You can either fix x direction or you can fix y direction. So if this is my x and this is my y, so which one you will fix and which one you will iterate? Or it doesn't matter, whichever way I do. Sorry? Question is not clear?
Yeah, it's clear actually.
Question is clear?
So,
Okay.
no, it doesn't matter as in, so it's actually so each direction is independent, right? TDM.
So whichever way you took, it doesn't matter.
Yeah, sort of.
Okay. Okay, like whatever we have discussed previously. So if you have, say, suppose you are taking TDMA along the y direction, and then you are iterating over the x direction. So like x direction is your Gauss Seidel. So along x I am taking Gauss Seidel method, and along y I am taking TDMA. So along y I essentially have only Neumann conditions. So if you try to apply TDMA, then the matrix is non-singular, right? So you just won't get any solution. Only for this particular type of boundary conditions, along x is where you have Dirichlet type of conditions. So TDMA works better, like the matrix will be non-singular. Your Scarborough will be satisfied always for Dirichlet type of conditions. So for this particular case, only this particular case, if you take TDMA along x direction, like only along the x direction you can take TDMA, and along y you iterate the Gauss Seidel, you will get a better converse solution instead of the other way around. For this particular case, otherwise in general it may not depend. It depends. Again, the question again is, say suppose you have okay, maybe I can ask you this question: which of these two methods you think is faster computationally, or at least will give you a faster solution, Gauss Seidel or the TDMA?
TDMA,
because
read about TDMA.
Yeah, it doesn't have to do an iteration, so you just directly get a solution. So
yeah.
So the preferred way is the one direction. If one direction has more number of nodes compared to the other direction, then the one which is having higher number of nodes is what you choose for TDMA, and the other one will go for Gauss Seidel. That could be one way. Boundary conditions could be one way. Other than that, your answer shouldn't be actually changing. Only for this particular case where you have Neumann conditions, your TDMA matrix becomes similar, so you will not be able to solve. Otherwise, this will work. We'll actually solve this. Okay, I'm not going to solve them by hand. Maybe I'll show you the implementation. So, like, how do you do it in code? The last question is essentially the one we have done maybe like 2 weeks back. It's the flow between two parallel plates. Then we have observed something like if you use Gauss Seidel method, your error and tolerance are kind of related. Like whatever tolerance you keep, depending if you refine your mesh for the given tolerance, the solution might become like it might not converge. So, but then we discussed like if you use a direct method like TDMA, it will solve to the level of mission precision, so you wouldn't face such issues. Maybe I'll show you. Just we'll take some demonstration of that. First we'll go with the TDMA. It's too big. So these are the coefficients I am taking for the normal TDMA. So A, all the A coefficients I am taking as 4. B is the phi I plus 1 coefficients I am taking as 2, and phi I minus 1 I am taking as 2. Okay, the first obvious question I should be asking is, does this satisfy Scarborough? So your A and B, sigma A and B is by AP if you do. This is the kind of thing you usually get. It will be equal to 1. So this is the case you will get for Neumann conditions. So it might not, but okay, we'll still go with this problem. So if you TDMA implementation is straightforward. So I'm just declaring two variables, P and Q. So our original equation is Phi equals Pi times Phi plus 1 plus Qi. So it is something like Phi is given by, maybe I have written this down, okay. So for initial value P0 is equal to B by A, and then Q0 is given by D by A. Again you just iterate from I equal to 1 to n. So like I equal to 0, I have already given the initialization. So Pi is given by in terms of Pi minus 1. So I is given in terms of I minus 1. Similarly for Qi is given in terms of Qi minus 1. So while you iterate, you will eventually get all the values, and for the last cell Phi is essentially equal, Phi is equal to Q for the last cell. So once you get the last value of Phi, then you iterate back. So your Phi is given by this equation. It's like you have Phi is given in terms of Phi plus 1 and Q. So Phi is essentially Pi times Phi plus 1 plus Qi. So you know the last cell value, so you'll get the value of, so if you substitute n minus 2, so you'll be getting the value of n minus 1 and go on till you get all the values, and then you just return it. So like TDMA is straightforward. Now when we have to do line by line TDMA, now we have additional coefficients. So like in addition to B and C, we are now having an additional coefficient. Okay, we have A, B. A is the coefficient for Phi, B is for east cell, C is for the west cell, D is for north, and E is for the south cells. So now D and E are the additional coefficients. So now what we have to do in line by line is to fix one direction and then take the TDMA for the other direction. So these are the four coefficients that will be going to my TDMA solver. So I've just written another function, sweep I is like, this is to fix along I direction, or you can fix along I or J depending on your direction. What does sweep I do is it just takes the coefficients. So when you are fixing along the I direction, it will take the coefficients from the J. So okay, this is sweep J, so this is sweep I. If you want to do along the I direction, you fix just the J coefficients. So your AI will be Aij, Bi will be Bij, Ci will be Cij. Now that your Di will have terms coming from the north, south, as well as a constant term. So your Di term will have contributions from, this is your north cell, J plus 1 cell, and then you will have from J minus 1, and this is F is a constant term. And for the boundaries, you need to appropriately remove, delete the terms. Essentially, the coefficients will be 0 for the boundary terms. Say for the north boundary, you will have J minus 1 coefficient to be 0, and for the south boundary, you will have J plus 1 coefficient to be 0. Once you get all these coefficients, you then send these coefficients as the normal ABCD to the TDMA so that it will solve. So that is exactly what, like, that's the only difference you make here. You take all the 6 coefficients. What sweep I does is, out of these 6 coefficients, it will just get those 4 coefficients that are required for the TDMA to solve, and then you, once you get the values, you update this value of phi, and then you get the error, and then you keep on repeating this. Like this is a Gauss-Seidel loop. It's a familiar loop, so you just repeat it till your specified tolerance value. So in this particular case, I've just taken both x and sweeping both x and y directions. So like for one iteration, I'll take x, and for the other direction, like for all even, I'll take I direction, and for all odd, I'll take x direction or something like that. But it's up to you. Like I just wrote it so that just for a demonstration purpose. I think line by line is clear, right? Or if you have any queries, you can maybe. So I guess this is clear then. The next question is when we are solving for the parallel the flow between two parallel plates. This is the same code we have done previously. The only difference is this, that now I have added TDMA here. So when you add, the code is again straightforward. So P0 is B0 by A0, and Q0 you get, and then you iterate your P and Q depending on your Pi minus 1, Qi minus 1. Once you get all the values, you just put your phi equal to q, or here the velocity n minus 1 equal to q n minus 1, and then you do the backward propagation. So you get all these things. So now if we compare this with the analytical solutions, so initially everything is converging. So this is for say n equal to, I guess, around 10 points. This has converged. So for the same tolerance, so if I say increase the number of grid points to say 20, so you can see that it is slightly different. So the analytical is matching with your TDMA, but then your Gauss-Seidel method has kind of deviated from this. This is essentially because your tolerance is, like when you increase your number of grid points, you have to increase your tolerance as well, so that it will be able to capture even smaller ones. So okay, even I kept a tall value here, I passed in a different argument. So maybe if I reduce the tolerance to say 10 power minus 6, then again the Gauss-Seidel will kind of converge to TDMA. So you have to be careful with your mesh size and tolerance in case of iterative methods. For a direct solver, it doesn't matter much. So I think that is clear. Now we have around half an hour. So if you have anything, we can discuss on. If you have any particular questions on this. I think this is clear. So you have any questions for this, or this is clear? The line by line method and the normal TDMA method.
Yeah, so I think this is my question still now, but I just want to ask, so we use TDMA like from now, is it like we use only TDMA to solve all the equations?
I mean, we will be using Gauss-Seidel mostly. So like you see the like line by line is fine. Even in line by line, when you go to 2D problem, you are actually using a Gauss-Seidel plus TDMA, right?
Yeah, I understood. Like one point you said that depending on the boundary conditions and depending on the number of points, and this Gauss-Seidel and TDMA are favorable. So you need to choose between them. That's what I have.
But eventually we will be using only, like for the remaining course, we'll be mostly using Gauss-Seidel. Like we won't be using TDMA much. If you want, you can, but Gauss-Seidel is kind of easier way. You just, I mean, implementation wise, it is much easier for the course purpose.
I can see that.
But then I think he has also discussed about successive over relaxation, under relaxation. If you have gone through
Not
the
yet.
lectures.
I don't think it's not yet. It's mostly still a TDMA.
Okay, then maybe we'll discuss that. Maybe I'll put some questions
next week.
Next week, yeah. The circular TDMA is clear, right? That is something very similar to the problem you are mentioning.
No, but since we haven't taken any these algebraic courses where we solve periodic problems and everything, even if you would have taken FEM, even in FEM, if you're solving the problem, you don't have boundary conditions. The system, it's like more symmetric. It is symmetric. I mean, it is singular matrix. You don't have boundary conditions.
So you have something of this sort. Say, so this is your some 2D problem where you have some heat sources, so some infinite array, something like this. So you just take this as a symmetry plane, or maybe you can, if the heat transfer coefficient is same on top and bottom, you can just take the quadrant and then used to solve for this particular portion. That's what you are saying, right?
Yeah. I mean, so in finite element method, you essentially
Yeah, you can
have
just put a
this.
symmetry plane.
Yeah, you have these grids, and you have this connection. You're trying to extrapolate the function values, right?
Mhm.
So over there, just charging my laptop.
Yeah.
Yeah, even there, if you have this, this is one problem which we have faced, and there is no solution in any paper. It is quite obvious, like for you, because you do this, like you set the values, you've been trained, or you learned this. But we took us a lot of time in, because I don't think even in papers while dealing with this problem they don't mention that we are actually, we will specify one of the points value as 100, or we take some value because this has the generated linear system has this property, and we can't solve it. Have you found any papers which actually mention that actually?
No, no, not really. It's just some kind of accepted standard kind of thing.
Do you understand what I'm trying? Yeah,
Yeah, I
exactly. It's
understood.
accepted standard,
It's some
and you
kind
don't
of
say,
unsaid.
you don't
Yeah.
don't see it at all. No, you don't see it at all. That's the problem. Yeah.
So I'm actually thinking of taking up this periodic flow, but I don't think it will be relevant to most of you here. So with circular TDM, if circular TDM is fine, then yeah, the next week starts with unstudy. So maybe I'll take an unstudy problem. We will not be I don't think 3D will be coming even. So I don't know how many of you are planning to take an exam.
There are only two people, so I don't.
Oh,
have
only two
anything.
people. Okay, everyone left.
I may take
No,
the exam.
only two people joined. Three people joined today.
Okay.
Yeah, no worries.
So someone said you'll be taking exam.
Yeah, I may be taking the exam.
Okay. So maybe then in exam you won't be asked any coding questions, so you might have to practice by hand, solving them by hand.
Do you use any of this in your research, Kumar? By the way.
No. As of now, I'm not using. I'm just learning. Maybe in future I may be using. So I'm just.
Are you a bachelor student or you a PhD student?
No, I'm a master student.
Sorry.
Okay. So great, you'll be using it at some point.
Yeah.
And then yeah, so I don't know if you're following the reference given in by the professor. So it's numerical solutions of fluid flow and heat transfer by Patankar. Maybe the title is wrong, but the author is Patankar, that is for sure. So he discusses most of these. I think almost all the problems taken in these sessions are from his book. If you want to refer the textbook, you can go through this textbook.
So I mean, I'm not sure. Maybe in the future sessions, you told me you don't use any open source or any commercial software. You don't use commercial software. You told me.
Yeah, that is for my personal. Okay.
I understand.
Yeah.
So, do you use any open source softwares?
It's like if you just want a solver, I use some C++ codes that are already available, like provided by some orders, just to solve some set of equations. It's like you don't have to write this TDME always, right? There are some optimized solvers that you use directly.
Exactly. Yeah. So in C++ there are so many. So what I want to ask you is, then there must be some very famous open source softwares based on whatever the course we have been dealing with. But like the course is very fundamental, and there we're not solving very big problems. We're just trying to understand the basics. Which I understand that. If you have any experience with a good open source software, I mean, a good. Why I'm saying is good is it could not be famous. And OpenFOAM is very famous, but you have to create folders, you have to do all that stuff.
Yeah.
same thing can be done in Python, like, or some other software which is much simpler to use and easier to research, as in small scale problems. You
I
understand
think
what
there
I
are,
mean?
I understood, but I'm not aware of any general source software. I'll speak with the professor once. If he has any, then I'll inform you. Like for domain specific problems, like for the area I am working on, say I am working on batteries. So there are specific open source for that particular battery itself.
Well, they essentially should solve FEM problem, right?
I mean, yeah, it is an FEM problem. Even battery use it's an FEM. But then you just don't use FEM. You use a combination of finite element plus FEM. So you just don't use one solver. So there are some things optimized only for that particular problems. So I think
So,
similarly there might be something similar for different domains.
okay, so one thing I want to ask you is, but one thing I want to ask you is, can you, if it is possible, because you must be reading so many papers day to day life, and this is very basic course. So if you can see what is like, if you like, the research in this area has been going on for so many years, so there might not be papers which are very easy to now which are being published. Like there are very little increment which they actually say maybe they will extrapolate the fee using some maybe
Some new
parabolic
function,
function.
yeah.
You understand? What
Understood.
I want to ask is, can we take one of those papers, any one of those papers which are published maybe last 4 years?
Okay.
Okay, maybe not explain everything. Maybe can we take very one of the most simplest problems which we can actually discuss, or maybe if you can, maybe you can. What I want to do is you can take any open source software which you say you don't have any experience with. So what I want
Yeah.
to see is, okay, this is what the course is dealing with. With SPH, I can actually explain. If I take a course in SPH, I
Okay.
can actually explain to any kind of paper. I can make it very simple, and I can do that. Okay. What I want to ask you is, can you take any one of those recently published papers? Maybe take one problem. You don't have to solve it. Maybe just explain. This is what we are dealing with. Maybe at least the flux, till the flux derivation. Maybe big problem or maybe small problem. Just for 15 minutes.
Okay, so essentially
Okay.
want to see an application point of view, or like novelty in the application or in the method itself.
Anything, method or application. Because I want to
I
see,
mean,
because
all these
this is
problems
something
are
I'm
from the
using.
papers. These are from this circular TDMA is from a paper of, maybe it's an old paper, but still there is one paper on this.
Yeah. So I want
Everything is a
something new.
paper, something new, right?
Of course. No. So first you publish papers, then they get into
Then they
books.
get into
That's
books,
how it
yeah.
works. That's how it works.
So maybe we
So can
can,
we?
okay, I'll speak with professor for some nice example. I have worked on batteries, but I don't think it will be relevant for most of you.
No,
Maybe
no. I
from
think it's
illustrate
the same.
example.
So for battery, you might do ion. I don't know what exactly
No, no, no,
battery
no.
has.
We just take the
Say
thermal. If you just take the thermal problem, it's again the heat conduction equation, anisotropic heat
exactly.
conduction
So we just
equation.
say, oh, this is the battery. This is the geometry I'm dealing with.
Yeah,
Battery, heat, flux, boundary conditions.
we've already
If you
discussed
can
that.
take all, huh?
We've already discussed that. I'm just waiting because it's an axisymmetric problem, and I think axisymmetric is not discussed, right, as of now, till week
No,
6.
not. I don't think so.
Okay,
So
only
he's
for
still at
Cartesian. Only for
still at
Cartesian.
solving the diffusion equation, 2D diffusion equation, 3D diffusion equation, using different Gauss seidel, TDME. That's how where he is now. So
Yeah.
maybe next week he's coming up. So
Huh.
we have 6 more weeks if I'm not wrong. Yeah.
Yeah. So
Not
once
now.
this
I'm
is,
not saying don't do it now. If you can, essentially maybe 4 weeks down the line, if you can actually,
maybe we'll
because
take
I
one
want to.
extra class. Like after this, all the sessions are over. Like it's a 12 weeks course. So the last week, on the final week, we can have this.
We can do that as well. So
Like
see
by
what.
then, simple will also be covered, so that it will be more relevant.
Yeah.
If we can take some better
Exactly.
example.
What I can maybe. So what I would love to do, or any, to make this course much more strong, is if you take any SPH course, I can actually take 2023 paper, and I can literally maybe solve in 1 hour some new problem, and maybe I can even publish it. So it's not that SPH is very new. I can add
Okay.
that maybe we can take a new problem, and we can solve it. You don't have to publish it. At least I want to see it, but this is very much new to see. This is how applied it is. Maybe it will make me understand more in research point of view, or maybe
Yeah,
whatever you have
understood.
published, maybe what published, you might have published some papers. You can take one of those papers that must be recent, because you're a very new PhD student. You can maybe discuss one of those problems as well. That is also good. What I want to do is, if you can teach us some open source software, maybe whatever problems you have solved, maybe that pressure difference parallel plate problem, we can take an open source software, solve that in that software, because it will take us a lot of time to write a software, new code for others now. So we at least in this area, SPH I can write, but So we can easily take that. Maybe I want to solve some. Maybe I'm teaching a course in fluid mechanics. I want to do a parabolic, periodic, polynomial flow,
Okay.
right? Or some other kind of flow, shear flow. Okay, I can easily take it and code it up in this open source software and I want to show, using FVM. I think this is doable if I'm not wrong.
Yeah, doable, but the only problem is we'll do it in the last. It's like it is
Last,
slightly off
exactly.
from the course, so we'll do it at the last class.
No, yeah, it is off, but it's just how what computational exactly it should be. Like computational, you have to solve it.
You have to solve
Which
it by
we're already
user.
doing.
Yeah, yeah.
No,
So
which we're already doing. Which you're already showing us codes and everything. So what it solves the
I actually discussed this with the
purpose.
professor. He was mentioning like it's better if you do demonstrations with your own codes than an open source software. So I was just going this way.
Exactly, completely fine. And what I'm saying is, if you can do it for only 15 minutes, because
Yeah,
it
yeah,
will be much
understood.
more. It will be very fruitful to see. Yeah, this is something. I mean, maybe in your 10th you might be doing Newton's laws, but you don't know where you apply. Just
Yeah, yeah.
frustrating to learn this stuff. So I understand where we can use this, but just want to. It's easy for us to get started.
Yeah, sure.
Yeah, not now. 6 weeks from now, like the last class, even that is possible. If you have time, maybe.
Yeah, like, if the last session doesn't be some, you can ask for an extra session if some of you guys would be like to attend. So we can take one extra session and then we can do it.
Okay, then I think.
Yeah, if you don't have any doubts, then we have like okay, it's almost 10 minutes. Okay, then we'll just conclude.
Yeah. Okay. See you. Thank you.
Thank you all.
Thanks.